So do you have a pointer?
Yes.
This one, right?
Yep. But if you want to point to anything in particular, like
Right.
on your slide, then you have to use a mouse. 'Cause
Okay.
That's what the lecture recording picks up.
Okay. You want
This one has, like, if you want to just show
right,
them really
right.
quickly, but this
it
won't.
won't show. All right.
Right, right. And then you can move your slides here. Susie is the AV rep. She's over there.
Sure.
She's going to just do the lab, switch it from you
So
to...
this is to advance
Yep.
the one that you can't see anymore.
Yeah. Yeah.
All
That
right.
one over there.
I'd rather speak here than to have
Okay.
the thingy.
Sure. So I'll just turn this off for now,
Yeah.
but for if Maria wants to do it.
Yeah, I project, so. And I'd rather
Well, make
stand
sure
there
you
so I
do-
can see what.
Yeah, make sure though you do speak in here, because then otherwise they can't hear you.
Yeah. Okay. Hi, everybody. If you can please sit down, we're going to get started because they start recording at 2 p.m. on the dot. Welcome, everybody. My name is Walter Palmas. This is the Evidence-Based Medicine Seminar, and I hope you have a good time doing it. This is actually extremely important. The idea here is not to give you a very comprehensive review of biostats. Rather, the idea is to make you ready to pick up a medical journal like the New England and go through articles and read them without major difficulty. So we try to make you comfortable with the basic skills of reviewing the evidence. And that goes from observational studies to randomized controlled trials, including the more complicated non-inferiority designs. Okay. And it also includes meta-analysis. So again, the idea here is not to teach you how to run statistical tests, but rather to be comfortable picking up a journal article and going through the methods section and then understanding the output in terms of the analysis they performed and the graphics, the usual tables you're going to encounter. So the main idea is that you need this in your day-to-day medical practice. And it cannot be emphasized enough how much this matters to you. You need to be comfortable with this when you review data for a given case to help your patient. Many of you are going to go into public health, so you're going to need the vocabulary to communicate with other people. Many of you are going to be members of the institutional review boards in your institutions, so you're going to be responsible for the protection of human subjects who are volunteering for medical research. And if you think that can be taken for granted, you will actually be sorely mistaken. It's up to you guys, it's up to the next generations of physicians to actually make it better than we ever did it. And it's actually up to you to identify the areas for future research and to fight for the funding for that research. Because for the most part nowadays, the research agenda is being driven by private funding, and that doesn't necessarily pay for the research we need. So if you don't understand the science of what you're discussing, you're not going to be prepared to advance the appropriate agenda for your patients and for society. We don't really have a perfect textbook for you guys, so what we try to do is to put together lectures that are fully informative and then have the small group sessions. The small group sessions are mandatory. The reason for that is that it's your unique opportunity to actually interact directly with somebody who not only is a evidence-based expert, but also a practicing clinician. All the people who precept the small group sessions are people who have additional degrees, such as MS in biostats or MPH degrees. Some of them actually have a doctorate, and everybody is a practicing clinician in their own field. So it's a unique opportunity for a smaller group of people who can actually get together and ask any questions they want to ask. I put together a list of additional reading materials that will be posted chronologically together with the materials for the lectures and the small group sessions. And if you have any questions or any comments, feel free to email me at WP56. I'm the only Palmas in Colombia, so I'm easy to find. And I'll be delighted to review the contents of those reading materials. So each small group session will come with homework. Please do it. The first small group session will be next week. And please come with your answers. It's not a test. The idea is that you learn best when you have to answer by yourself, and then you correct your errors and you get to ask questions to the expert. So please bring your answers and be ready for a conversation with your preceptor. At the end of the session, we're going to give you a brief version of the answer to each question just for your own record. I also put together a very brief EVM glossary that's in the main document that was already emailed to you. The idea is just to keep in mind basic concepts you may encounter here and there, and I also included a checklist for every type of journal article you may encounter in the future. And I put that together for the medicine residents over the years. I am in charge of teaching them evidence-based medicine. I do a journal club with them. I do a seminar that gets repeated every year for the medicine residents. So I generated that for them, and they find it very useful. I hope you'll find it useful too. So we'll have 11 lectures. There will be 4 small group sessions. And at the end, I'm going to do a brief review session with you guys. So the idea is that the test is not going to be torture. The test is just meant to check for very basic skills. And nothing that is not actually addressed in the lectures and then reviewed in small group sessions and then you get reminded of in my review session will actually appear in the test. Okay? There is no way anybody can fail if you come to the lectures, if you participate in the small group sessions and then attend the review session. This is not a trick. The idea is to provide you with tools you might find useful in the future. When I did my master's in biostats, there was one particular guy who gave the best lectures ever, and to this day, when I run the analysis for my own papers, I still go to the notes from his lectures rather than going to a textbook. So if anybody ever tells me that they have used notes from this seminar in the future, that would be a pleasure to hear. So the final test will be on October 6th at 2 p.m. It will be 30 questions. One of them is a little tougher than the others, but we'll eliminate that from the scoring if too many people don't get it right, so don't worry about it. The meaning of that specific question is that we want to see how far you've gone in understanding the issues involved in evaluating the evidence. Again, my email address is wp56@columbia.edu, so please don't hesitate to email me with any questions. So we're just going to go into the first lecture right now, so there will be enough time for questions and answers at the end. Maria de Miguel is an expert because she's a fantastic clinician. She's got a master's degree, and she's been in charge of our primary care residency program for many years now, and she has educated a generation of fantastic new primary care physicians.
Thanks. It's great to be here. So I'm going to try to make this lecture, which I know for some of you is an introduction to epidemiology. I'm going to try to make it interesting and fun and get you guys to think a little bit about how you would design a study. And I want to say off the bat that I'm going to keep it relatively simple. So if any of you guys have taken epidemiology courses or biostats courses, you may find this kind of straightforward. But hopefully most of you will find it useful. Because as Walter said, I'm a clinician and I don't do research as my primary day job. So I feel like it's really important for doctors to understand evidence, even if they're not going to be doing it day to day, because not only will you have to teach students, you'll have to teach other residents, you'll have to teach other doctors, but you'll have to most importantly be able to communicate with your patients. And we need evidence every day, all day, to be doctors. We need to refer to the evidence and we need to use it in our discussions with patients. So some of what we're going to talk about today is how to translate data into meaningful concepts for yourself and for your patients. So I have no disclosures, and as Walter said, it's really important for people to tell you if they do have any economic interest in what they're presenting to you. So what we're going to go over today is a little bit just thinking about how we prove cause and effect in medical research, what types of research studies we have at our disposal to prove cause and effect. And we're going to go through a little bit of the reason why we can't use interventional studies or randomized controlled trials to prove everything, and when we would use different kinds of observational trials and what an observational trial is. And we're going to go into some detail about the two main kinds of observational trials, the cohort study and the case control studies. And we're going to talk about, for each of those studies, how do we measure that effect? How do we measure that cause and effect relationship, or get as close to, as possible to proving a cause and effect relationship? What are the sort of tools that we use to measure it? In the cohort study, we're going to talk about something called a risk ratio. And in the case control study, something called an odds ratio. And we're going to talk about a couple of other clinically useful concepts, which are basically ways to use the numbers to understand how much disease we can expect and how much benefit or harm we can expect from different treatments. We're also going to talk about the limitations of observational studies and how to sort of think critically about a study that you're reading. Because again, this course, we're not trying to prepare you to go out there and do research tomorrow, because it's a much more complicated endeavor than that. We're trying to prepare you to be able to read a study knowledgeably and be able to use the data in your life as a doctor and talk about it with patients. So in general, fact and truth in medicine comes from observations. We usually notice that something is happening, something seems to be related to something else, and we need to try to prove cause and effect. So as an example, we might notice that people who have sort of unhealthy lifestyles might end up having heart attacks. So there's clearly something about the unhealthy lifestyle that leads to the heart attack. And we might maybe make the assumption that it's drinking alcohol. So maybe you notice that people that tend to drink a lot of alcohol tend to have cardiovascular events like heart attacks. So it'd be easy to stop there and say, let's just tell people not to drink alcohol and they won't have heart attacks. But there might be other causes that come along with that alcohol or that unhealthy living that are the real cause. And what we're going to talk about today is how to turn an observation into a well-studied and a well-proven cause and effect relationship, and how to avoid errors in terms of observations. So just a little bit of terminology. We're sort of getting into the realm of epidemiology here. And epidemiology is the study of diseases in populations. So we're not just talking about I see a patient and I see that disease. We're talking about watching what happens in a population. And ideally, to answer population level questions about disease, we could study the whole population. That would be ideal. If we had data on everyone and we could study the entire population, we would get great answers. And some countries that have sort of national registries of disease produce a lot of great research because they are actually keeping track of their whole population. Clearly, we don't have anything quite like that in the US. So what we're often doing, usually doing, is taking a sample of the population. So a lot of times in studies, we'll talk about what is the sample like, or what is the subset of the population that's in the study. And how we select that subset of the population to study is very critical to the study and to the validity of the study. So most importantly, that sample that we're choosing should reflect the general population that we want to apply the results to. So that's like a basic concept that you can apply, you can think about when you start looking at any study. Does the patients that they included in this study reflect the patients that I'm thinking about treating? So in general, a lot of studies over the years have not included a number of minorities that are present in the general population, or potentially where you practice may be a very different ethnic or racial minority compared to where the study was done. So that's an example of thinking critically about, does the study results reflect who I'm going to treat just based on the sample that is included in this study. The other terms that we're going to use, so we're basically trying to prove the relationship between a cause and an effect. So the cause can be often called things like an exposure, which is kind of a generic term. It doesn't imply harm or benefit necessarily. It's just something that you're exposed to or a group is exposed to. An intervention sometimes is used as the term, which it implies that there should be benefit or that we're doing something to people. But either of those terms can be used in different types of studies. We'll talk about when you would use which one. And the effect can be a disease or an outcome. Outcome is obviously more general because maybe you don't know if it causes harm or a benefit or a disease or no disease. So outcome is sort of more of a generic term. But just so you are sort of comfortable with these interchanging words that we're often using. And this nomenclature of the 2x2 table is also something to get comfortable with. You'll be asked in your small group to set up a 2x2 table. And when you're calculating things like risks and risk ratios and odds ratios, the assumption is that you're setting up your 2x2 table like this. So basically, the exposure is usually on the side, and whatever the outcome is on the top of the table. And these letters are assigned in sort of a meaningful way, A, B, C, and D. So when you're setting up your 2x2 table, just think quickly, do I have it in this sort of setup? Because usually this is sort of a general way that these tables are set up. Occasionally you'll see people change it around and make it confusing, but in general it's usually like this. So when we're trying to prove cause and effect, if we were in an ideal situation, we would start with a sample. We would be able to know that part of that sample was being exposed, and we'd be able to measure the exposure and know what the exposures are. And the other half would be unexposed. And then we would go forward in time and see how many of those people get the outcome. And we would measure that in the two different groups. And we'd be able to say, in the exposed group, this number got the outcome, and in the unexposed group, this number got the outcome. And we could compare those results. So one of the basic concepts in terms of an ideal study to prove cause and effect is that it's prospective, which means that at the beginning, no one has the outcome. The exposure happens, and then we see who gets the outcome. So cause would come before effect. It's basic concept that cause comes before effect, but we don't always have the ideal situation to study things that way. So ideally, people would start out unexposed in the sense that ideally we'd be able to measure and understand the exposure. That sometimes is the case, sometimes isn't. Also, again, like I mentioned, ideally the sample that we are choosing to study reflects the general population. Ideally, we'd be able to randomly assign an exposure to the two different groups, that you don't choose to be exposed, or you're not exposed because of sort of natural conditions, that we could actually control the exposure. We'll talk about why that's not usually often possible. But ideally, that would be the case, because then we could randomly assign people to groups. And the reason why the randomization part is helpful is because when people choose to be in a group, meaning like say I choose to smoke, I often have other things that I choose to do that go along with the smoking, like the unhealthy lifestyle. So I talked about like someone who might be drinking alcohol and smoking. And when we try to see the effect of those things, sometimes it can be very hard to tease out if it's from the alcohol or the smoking. And so when we do a randomized control trial, part of the reason we randomize people to different groups is so that we don't have those sort of extra causes coming along with the exposure that we're trying to isolate. So in any experiment, we really want to isolate that exposure. We'll get into this more. So again, ideally, no one would start out with the outcome, so you're doing a prospective study going from cause to effect. And ideally, the outcome that you're looking for happens relatively quickly, so it doesn't take forever to measure it, and it's not a rare outcome, so you're seeing it happen in the population. And ideally, the exposure and outcome are not harmful things that you wouldn't be able to do to people. So that was sort of a concept of like what would be ideal. So interventional studies, which is what we hear about a lot, which are randomized in medicine, randomized controlled trials, is one version of it that you're going to hear a lot more about. In an interventional study, something is being done to the group with the exposure, so that the researchers are actively doing something. And the reason why that's important is, first of all, When you're getting your sample, you have to recruit people. So again, thinking about who's being recruited into a randomized controlled trial is part of critiquing a good randomized controlled trial. Is this a good sample of the population? It also is, at the beginning, a randomized controlled trial. The first step is to exclude people, because we want to try to limit the number of possible confounders or possible other things that come with the exposure. So one of the first steps of an interventional study is to exclude other things, people that might sort of complicate the analysis. And again, this limits the potential applicability because it may not adequately reflect your general population. The second step in an interventional study would be to randomize the intervention if it's a randomized controlled trial. Again, being able to limit the amount of other exposures that would come along with the main exposure. And the third step then in an interventional study is to test and monitor and watch a group of people for a period of time to see what the outcome is. So it takes time, and it takes money, and it takes monitoring. And the applicability to real life is one of the main limitations to a randomized controlled trial, because you've controlled this experiment. You've controlled who got into it. You've controlled how they receive the exposure. You've monitored them really closely, and that may or may not be real life conditions. So that's one of the main concerns about an interventional study. Sorry, stay close to the microphone. So the other big concern about an interventional study is just the fact that you're doing this thing to a group of people. So now's when you guys get to throw your hands up. Anybody think of a situation where you couldn't do something that you might want to study that you couldn't do to the group of people? Yeah. Infection, right. So you couldn't cause the infection in a group of people. You want to watch that happen. That's where epidemiology obviously started, with watching epidemics of infectious diseases. What else can we not do to people? Yeah. Okay, so like a natural, so that's an example of like a physiologic study. So watching sort of, you want to see how physiologically something happens. So like if someone has, for example, to generalize it a little bit, maybe something like hypertension, like what outcomes happen when you have high blood pressure? Do you get strokes or heart attacks, things like that? So those are like natural physiologic studies. Yeah.
The exposure is harmful. No, it's harmful.
Good. So like, give me an example. Yeah, so good. So obviously like Tuskegee would be an example from watching people, the natural course of a disease that you've inflicted on someone. So things like harmful either exposures in the environment, harmful exposures that people might do to themselves, like behaviors, and then also things like, so we mentioned physiological, like social and environmental phenomenon, right? So poverty, for example. How does poverty affect health? That you couldn't make someone poor and then watch what happens. You couldn't like expose someone to, lead in the environment and watch what happens. And then also the other situations where interventional trials can be difficult is if the outcome is very rare. So for things like lung cancer, for example, it would be very hard to, not only could you not do the intervention because it would be unethical, but cancers take a long time to develop, and certain diseases take a long time to develop and can also occur very rarely. So for rare diseases, interventional trials can be very difficult, but also if the disease takes a long time to develop. So for all of these reasons, we need observational trials in medicine, even though observational trials have their limitations, and we're going to talk about what those are. We're going to need observational trials to answer some of the questions that we just kind of talked about. Physiological phenomenon, do social and environmental phenomenon have effects on health? We need to think about how harmful exposures or harmful conditions produce disease, because we need to know how to potentially intervene. And we need to think about rare diseases and things that take a long time. So we can't always design an interventional study. So we're going to go through two of the main kinds of observational studies in some depth, cohort and case control studies. And the title of this talk was Longitudinal Cohort Studies, meaning going forward. And just so you guys know, there's something called a retrospective cohort study. I'm not going to get into detail on that, but I want you to have heard the term before. We're going to talk about some of the situations where you'd use these two main kinds. And then we'll also talk briefly about what a cross-sectional study is, which is another form of observational study, but we're not going to spend a lot of time on that. So first, we're going to start with the cohort study. And a cohort study is basically where we think that there's some exposure that exists in the world, in the environment, that we want to see what the outcome is. If someone is exposed to something, do they develop a disease or do they develop an outcome of some kind? Usually it's something harmful. And we want to compare them to people who don't have the exposure. So the key thing with a cohort study is that it starts with exposure. Another term you might hear is that people are sampled based on their exposure or selected based on their exposure. So you start the study because you are an exposed person or an unexposed person, and you don't yet have the outcome. You don't yet have the disease. So the key thing about a cohort study is that groups, quote unquote, choose what group they're in, meaning no one is doing this to them. They are in that group because of, I don't mean choose in the sense of necessarily active. It may be passive, meaning that nobody chooses to have exposure to lead. But you are meaning that other things in your life come along with that exposure. So when we're thinking about possible confounders or the things that might come along with an exposure, we have to remember that in cohort studies, we didn't isolate that exposure. That exposure came with other stuff. And so we'll take the example of smoking. Again, we can't make people smoke. People choose to smoke or don't smoke. So what kind of outcomes might we look for if we're doing a smoking study? Just throw them out there. What does smoking do to you? Lung cancer? Emphysema? Life expectancy, so just like plain mortality? Sure, so physiologic studies about like how the lung functions in terms of oxygenation. Okay, and then I mentioned cardiovascular disease. So the point there is that the nice thing, or a lot of these things are very common. So COPD, cardiovascular disease, relatively common with smokers. So if we were setting up a cohort study and we were watching people with the exposure, we can expect to see some results over time. We're going to expect to see people get those diseases, and not ridiculously long periods of time. But cancers would be an example of something that actually would potentially take a long time, although lung cancer is one of the more common cancers that are out there. So you might actually see it within a relatively shorter amount of time. But there are some cancers that are incredibly uncommon that are associated with smoking, like bladder cancer, that would take a lot longer to get those cases over time. So we'll talk about when you might study those, how you might study those. And then we also mentioned that smoking comes often with other behaviors or other situations. So I mentioned unhealthy living. What else might come along with smoking? You guys think of it?
Alcohol.
Okay, so using other things like alcohol, other drugs,
Lack of exercise.
poor exercise. What else, like on a maybe more social level? Yeah, low socioeconomic status. So we know that smoking correlates with that socioeconomics. And a couple other things like education, things like that go along with that. So the point is that we have to take those things into account and think about how we're going to measure them when we set up a cohort study, because we want to measure all the things that we might think might come along with the exposure. Okay, so it's not that we can't do the study just because other things come along with smoking. We just have to think about them at the beginning and measure them. So the good things about a cohort study, that design is prospective. So it's a good approximation of a cause and effect relationship because we're starting with the exposure and the people do not yet have the outcome. So nobody's going to be included in our study who already has heart disease, COPD, or lung cancer. Say those are the three things we're going to study. We're not going to include anyone who already has that at the beginning. It's very real life, so we're not excluding large numbers of people in terms of the exclusion criteria, and we're taking people sort of as they come in their life. So presumably it's a little bit more real life than an RCT. Although it can, depending on the population you've chosen to sample, it still may or may not apply to the population you're thinking of. And the other benefit of a cohort is that you can study multiple outcomes. So we know that smoking has multiple potential health risks. So the nice thing is we're watching things as we go forward, so we can sort of at the beginning say, we're going to look for this, this, and this. We're gonna see if multiple different diseases come about. The bad thing, again, people choose their own groups. It comes with a lot of other things. And if the problem becomes if we don't think of a possible confounder, meaning like if something else might be out there that could be associated with both smoking and the outcome, and we don't think of it, it could affect our results. And then finally, the other sort of weakness or bad part of a cohort study is that we have to follow these people for a long time potentially, and we might lose people. So people might drop out, they might die, they might move away, we might not find out that they had that outcome that we were looking for. So it takes a lot of time and money and energy to run a cohort study, and even with the best intentions, we might lose people. So the one risk in terms of the validity of our results is if people drop out of the study based on or start having something to do with what group they're in, either exposed or unexposed. So say people are in the smoking group and they have sort of an unhealthy lifestyle. Maybe they also have a tendency to not follow up with stuff. So those people are actually more likely to drop out of the study than the people who are in the unexposed group. And that's going to affect our results. So how do we measure the effect? So basically we do our study and we want to say, did this have a meaningful result? Did this have a meaningful effect? Is there potentially a cause and effect relationship? And the way in epidemiology we usually say that we use the word associated because it's very hard to say we've proven that there's a cause and effect, and the terminology is usually that they're associated. And we want to say basically how strong is that association? Is the outcome very strongly correlated or associated with the potential cause or the exposure? And so we use a group of measures that are called measures of association. And in a cohort study, the measure of association we're using is called a risk. And a risk implies that you're looking forward, meaning it's a prospective study, that you started with just the exposure, no disease, and you developed disease. So what is your risk of developing disease? So again, going back to that 2x2 table where the outcome is on the top, the exposure's on the side, A, B, C, and D are assigned like that. The risk of a disease in the exposed is calculated by so A, or who has disease in the exposed group, over the entire exposed group, A plus B, and then the risk of disease in the unexposed would be C over C plus D. Pretty straightforward. So we're going to go through an example of a cohort study and just kind of how you would set it up and how you'd think about risk. So we'll think specifically about cardiovascular disease, and does smoking increase your risk of cardiovascular disease? So the way we start a study, a cohort study, is to think about exposure. So we're going to go out in the population, we're going to find 3,000 smokers and 5,000 non-smokers. So if you're thinking about your table, these two numbers are set at the beginning. These are not going to, this is how we start our study. And we're going to watch them for a year, and we're going to see who develops cardiovascular disease. So basically, who goes into these boxes? So in our smokers, out of 3,000, 84 of them developed cardiovascular disease. These people did not. And then out of our 5,000 non-smokers, 87 developed cardiovascular disease, and this many did not. So by just first glance, it seems like more relatively more people, a higher proportion of people in the smokers group, 84 out of 3,000 is a bigger number than 87 over 5,000, right? So it seems like cardiovascular disease causes disease. So we're going to talk about how to think about those results. You're looking at a paper in the New England Journal. How do we sort of understand what we're looking at? We're going to think about, is this a clinically meaningful result? And then the other key thing is, could the difference that we're seeing between these two groups be due to just chance? Could this just have randomly happened that more people ended up having cardiovascular disease in the smoking group? And this is where you use a statistical test for significance. This is where the p-value comes from. And you guys are going to have a lecture on that, I believe, tomorrow. So I'm not going to talk today about the statistical tests that you use to determine if your results could be due to chance. That is going to be a whole lecture tomorrow. And the type of statistical test that you use depends on the type of study that you're doing. So it's a whole lecture. It's actually a whole degree, but tomorrow you're going to get a lecture. The other thing we're going to think about when we're sort of critiquing a cohort study is, could there have been other reasons the exposed group ended up with cardiovascular disease? So basically, did anything else come with smoking? And then we're going to think about, is there a problem with how the study was designed? Basically, like, are people not following up based on which exposure group they were in? And could that have affected our outcome? So is this meaningful? How strong is the association? That measure of association we talked about. So there's a couple different measures of association relating to risk. We're going to talk about how to think about risk and how to sort of conceptualize it when you're talking to your patients and thinking about the study. We're going to talk about absolute risk, relative risk, or the risk ratio, which is the same thing. Attributable risk, which is basically also called the risk difference, and the number needed to harm and number needed to treat. We'll talk about those concepts. So the absolute risk is basically the amount of disease in the population. So in our 2x2 table, if we do the numbers, basically the A over A plus B, in the smokers, our absolute risk over 1 year, risk always has to come with a time frame because the study happened for a year. The absolute risk in smokers was 0.028, which can also be thought of as 2.8%. So you have 2.8% risk of developing cardiovascular disease over a year if you smoke. And if you don't smoke, your risk is 1.7%. So clearly the risk seems higher in smokers. The other important point is that just to remember that to be accurate, to be applicable to the general population, just remember that your sample has to reflect the overall population. There are ways to be testing that, but just to keep that in mind. So the relative risk, or the risk ratio, is another way of conceptualizing the comparison of those two risks. The non-smokers were 1.7, the smokers were 2.8. So the relative risk is just like what it sounds, basically dividing the risk in the exposed by the risk in the unexposed. Pretty simple. If the risk ratio or relative risk, they mean the same thing, is equal to 1, that means there's no association between exposure and disease. So if they were the same, if you had the same numbers, it would equal 1. There's no association. If the relative risk is greater than 1, then the exposure is associated with the outcome. So for us, we have 0.28. That actually should say 0.028, but it doesn't really matter for this. 0.28 divided by 0.17 is equal to 1.61. So the relative risk is 1.61. So it's greater than 1, so the exposure does seem to be associated with the outcome. And if it happened to be less than 1, then it would seem protective. Like if non-smokers got more cardiovascular disease, then smoking would look like it was protective. Pretty basic concepts. So the way to use relative risk is to think, or you could say, so smokers are 1.61 times more likely to develop cardiovascular disease over 1 year. Always has the time frame, always 1 year, over 1 year. And smoker, or another way to say this would be that smokers are 61%, so 1.0 would be 100%, so 61%, so 61% times more likely to develop cardiovascular disease over 1 year than non-smokers. Two ways of saying the same thing using the relative risk. So that's a helpful concept if you're, you're trying to convince someone to quit smoking and you're talking about the fact that you even over a year, you're 61% less likely to develop cardiovascular disease than someone who doesn't smoke. That's helpful. So another concept is the attributable risk, or how much of the disease in the population is attributable to the exposure. This is also known as the risk difference or the absolute risk increase. So pretty simple concept, just the risk in the exposed minus the risk in the unexposed, nothing crazy. So again, that 0.028 minus 0.017 would give us 0.011. And the way we would sort of say this would be, in the population, there's a 1.1% increase in risk of cardiovascular disease over 1 year that's attributable to smoking. So that's kind of thinking about the overall population. Or, you know, if you look at 0.011, that would be like 11 over 1,000, right? So you could sort of conceptually say it as 11 people out of 1,000 over 1 year get cardiovascular disease that's attributable to smoking. Different sort of ways of framing the same concept. Sorry, I don't know why that. So another concept that's useful is called the number needed to harm. And in this case, we're saying number needed to harm because we're talking about a harmful exposure. And there's studies where what you're looking at is an intervention or something positive, and you'd say number needed to treat. But it's the same concept. You could also, sometimes you'd hear something neutral that says number needed to expose. That would be like a neutral way of saying it. But it's the same concept. So a number needed to harm is to help us be able to say how many people would have to be exposed for one person to develop that disease. So this is calculated by doing 1 over the risk difference, the risk in exposed minus the risk in unexposed. Also, pretty simple calculation. And the answer here is 90.9. And basically what that means, I rounded up from 90.9 to 91, is that 91 people would have to be exposed to smoking for one person to develop cardiovascular disease. So that may be a helpful way of thinking about things. It might not be that helpful when you're talking to your patient, that 91 people can smoke and only one. But on a population level, that could be helpful because actually that's a relatively small number if you think about the whole population. And that's only over 1 year. So that's a short time frame. Always good idea to always should add the year. I should have put 1 year. So, and again, if this was a treatment study, you could say, and the outcome was a health benefit, you'd use the same formula to say the number needed to treat. So this is actually really useful when it comes to medications because we'll often say we'd have to treat such and such number of people with aspirin to prevent one heart attack. That's a useful concept in medicine. So going back to some of the limitations of the cohort study, we talked about what else might come with smoking that, again, we would have to measure, know about and measure at the beginning of the study so that we could control for them with the statistics. And then who did we include in the study? How did we find the exposed and unexposed people? And is there anything that came with how we found them that could also be associated with the outcome? So, for example, if we found our smokers by hanging out outside a bar, and we enrolled them in the study, and then we found our unexposed people when they were going to their doctor's appointment, there could obviously be a major problem with the comparison between those two groups, right? There's how we're selecting people to be in a study could potentially bring along with it unmeasured, unthought about characteristics. So we want to be really careful to know that the way that people were recruited into a study doesn't bring along with it other issues. So, for example, sometimes in studies to get controls, there'll be random, or even cases, random digit dialing. And that's an attempt to try to mitigate a little bit of that attracting people to studies based on other characteristics that they might have. So that's one potential way of trying to avoid some of the problems with the selection. And then the other question with the cohort study is who stayed in for the whole year and who was lost to follow-up. So one of the things you want to do in a cohort study to be critical thinkers about cohort studies is looking at the lost to follow-up rates and seeing if there was more lost to follow-up in the exposure group or in the unexposure group, and trying to think about, is it possible that the reason why people weren't following up had something to do with their exposure, because that will affect the possible results. Because if people don't follow up, we don't know if they got the outcome. And so those measurements of how many people got the outcome in the different groups is going to be skewed because if people didn't follow up. So basically what we just described is confounding and bias. So confounding is basically those other factors that come with the exposure and affect the exposure. We can control for these if we know about them and we've measured them. And you're going to talk about this a little bit more in the statistics lecture about how you control for confounding. But bias is a different problem. Bias comes with the structure of the study and who we included in the study. Who we include in this study, how we measure the exposure or outcome, and how we analyze the results. Bias is a big topic. There's a lot of different kinds of potential biases. But the important point about a bias is that it cannot be controlled for. So no number of fancy statistics can get rid of bias. So we'll talk about a few potential kinds of bias to think about, just some basic ones. So again, confounding is the things that can come with a person. So you smoke and you drink and you don't exercise, but we want to isolate smoking. As long as we've measured the other things, thought about them and measured them, we can control for them. And one of the simple ways to control for a possible confounder is to stratify the results, and I'll tell you what that means. Some of the very simple confounders that cause effects in most studies would be like age and gender. So you often see results separated out by age and gender. And this is an example of stratification to show you females versus males. And you want to see basically, are the outcomes very different in females versus males, because that could be a potential, that would mean gender is a potential confounder. And you can control for many possible confounders at the same time using regression. So that's also something I think is talked about in the, I'm not sure if she gets into it in the statistics lecture, but regression is a way to basically hold many different possible confounders the same so that you can isolate the effect of one exposure. It's a mathematical technique. But again, bias is something in cohort studies that, in any kind of study, that you can't control for. So selection bias is, again, are we including people in the groups in a way that, do we choose people for the groups that is different or could possibly be associated with the outcome? Or are people lost to follow-up? That's an attrition bias. Are they less likely to stay in the study based on their exposure status, and can that affect the results? So again, it's important when they're setting up a cohort study to think about biases that could affect your results. In the article that you guys are going to talk about for your small group, it's kind of an interesting study because it's actually a case control study, but who stays in the, or it's not so much who stays in, who was selected to be in the study and how is an important potential role of bias. So you guys are going to talk about that in the small group. So again, some of the other limitations to cohort studies, it requires a lot of people, a lot of time, and a lot of money, because usually you're sampling for an exposure, watching people over a period of time, and that can be a very expensive, large thing to do. So things like the Framingham study, a big cohort study, was a huge, very expensive, I don't know how many bajillions of dollars, study to watch people over many years and see what happens based on their exposures. So you usually need to have some idea that there's an association before you set up a cohort study. And they can be prone to confounding, so you have to identify and measure and control for a lot of different kinds of exposures. So cohort studies are very useful for certain questions, but can be very labor intensive. Again, some of the positives of a cohort study is that you can study exposures that can't be done to people, which is like a lot of different types of risk factors. You can study multiple different kinds of outcomes from one exposure, which can be very, very efficient. And you can calculate the risk because the exposure clearly becomes before the outcome. So Now we're going to move on to case control studies. And case control studies are particularly useful when a disease is rare or takes a long time to develop, because a cohort study could take too long or require too many people. So again, going back to our smoking example, if we're trying to study some of the rarer forms of cancer that are associated with smoking, say bladder cancer, it would take a long time and a ton of people to pick up some cases of bladder cancer. So it's much more efficient to start from people who have bladder cancer, who have the outcome, and go backwards and see what were they exposed to, and compare them to people who don't have bladder cancer and see what they're exposed to. So it's a much quicker way of doing an analysis and requires many fewer people. So just looking at what a case control study would look like, we would start with the disease. So we would, again, using the epi terms, we would sample based on disease. So the people would be included in the study if they had the disease. And then we would have to find controls, basically people who looked as much as possible like the people with the disease, except for the disease. And we'll talk about how we match controls, because there's different ways. And then we would look back in time to a time before they had the disease and try to figure out what they were exposed to. So the key thing about a case control study is it's retrospective. It's not going forward in time. We're looking back. So the hard part about a case control study can be choosing controls. So again, we want people who don't have the disease but are as similar as possible in every way to the people with the disease. Because again, confounding is going to be a potential problem also in case controls, meaning that people will come along with other things. Those smokers still might have had exposure to alcohol. They still might have had exposure to other potential toxins and potential behaviors. So we still have to think about confounding. And when we match or we find controls, we want to try to find people who are as similar as possible to the people with the case, with the outcome. So choosing the controls can be really difficult. There are different ways to match. So we could say, I have a man who's 50 years old and smoked, or I'm sorry, a man who's 50 years old and has bladder cancer. I'm going to find another 50-year-old man who doesn't have bladder cancer, and maybe they're the same racial ethnic group and the same socioeconomic class. So that would be a way to match, meaning find someone as similar as possible for the things that we think might matter, the things that we think might be confounders. Another way of doing that would be by group. So basically saying, in our group of bladder cancer patients, the average age was 65, and there was 50% males, 50% females. So when we look for a control group, we wanted to have those same characteristics. So there's a lot of different kind of fancier ways of matching. But just so you know that the goal is to have the groups look as similar as possible. So when you're critiquing a case control study, one of the key things is to think about how similar was the case group and the control group, and is there anything that was like really standing out, like wow, all the cases were men and all the controls were women? That would make no sense. But like, it's often a little bit more subtle, like the average age was a bit off, or race, ethnicity was off, or socioeconomics, or something like that. And then similarly, the matching with controls has room for bias. So where we get the cases and controls from, if it's different in a significant way, that could be a big problem. And this comes into case control studies more often because the selection bias issue, because a lot of times people with the disease are being found based on healthcare, like from healthcare settings. So you find your cases because they've been admitted to the hospital with cancer. And so usually the controls should come from something similar in terms of a healthcare setting, because otherwise you may have a very different type of person in terms of seeking medical care. So the other difficulty with case controls is going back in time and trying to figure out if the person was exposed or not. So this requires that the data either had been recorded in a medical record somewhere, or it would rely on something like an interview or a questionnaire. So ideally, a case control study is looking for exposures in something objective that didn't have to do with the person like remembering data. The ideal situation would be like we can look back into their, pediatric records, or we can look back into the data that was collected on them for some other purpose in the census or something by the health department. That would give us sort of an objective record of their past exposures. But that's often very hard to find. So, for example, if you were talking about something like birth defects, comes up all the time, where a child is born with a birth defect and the mother's being asked to recall what she was exposed to, maybe what she ate, if she smoked, and you can imagine that your memory might be very skewed based on the results. So if I had a perfectly healthy baby, am I going to think very in detail about what I ate and drank during my pregnancy? Probably not. But if I had a baby with a birth defect, I might be like really overly tuned into like what I ate tuna 3 times, and is that why I have a baby with a birth defect? So basically, recall bias is a problem where patients tend to recall things differently based on whether or not they have disease. And just spotty memory in general, in the sense that how good are people at remembering things that happened to them in the past. The other thing is that case control studies need to look at exposures at a point before the disease happened. So you have to be really sure that you're getting far back enough that nobody had the disease when you're looking at the exposure. Because you really want to know that that before and after relationship exists, that prospective relationship. So you may have to look way back in time to get to that point, but you're never 100% sure that, say, they didn't already have the cancer brewing when you looked back. It may just not have been diagnosed. So that's a potential weakness for case control. So when we think about case control studies and what we're going to use in terms of our measure of association, the problem here is that when we're doing the study, the disease already exists, so we don't have that temporal relationship clearly in terms of cause and effect. We're trying to sort of recreate that cause and effect relationship in the way we set up our study. So we can't calculate a risk, because a risk implies the risk of developing a disease, but the disease already exists. This is kind of like a subtle point, but it's important, because the only thing we can say from a case control study, the measure of association, is what is the person's probability of the fact that they had an exposure and they developed disease. So the probability is called the odds. So this is kind of like a difficult point, and I feel like this, again, takes many, many lectures when you're studying epidemiology, but the odds is different than the risk. It's not as strong of a measure of association. And in a case control study, we cannot technically calculate a risk, if that makes sense. So when we're calculating an odds basically comes from looking at the exposed and the unexposed. Again, cases and controls. So same setup of our 2x2 table, but here we're saying cases are people who have the disease or the outcome. Controls are people with no disease. So we didn't really call them cases and controls in the cohort study, but it's the same concept. And then also the exposures usually go on the side. So again, on the case control study, we're going to start with a set number of cases and controls, and we're going to see who is exposed and unexposed. But the A, B, C, D, you assign the same way. And then the odds ratio is basically the same concept as the risk ratio or the relative risk. Basically, we're saying what are the odds in the exposed group of developing disease versus the odds in the unexposed group. So one thing I want to point out is this, what I've put here is called is technically the exposure odds ratio, which basically means that for the cases, so for people who had the disease, what's the odds that they were exposed? So the odds that they were A, exposed over C, unexposed, over the odds that the controls, or people who didn't have disease, be the odds that the controls were exposed over the odds that they were unexposed. There is something called or I should say, when you have A over C, B over D, if you just do the algebra, this sort of simplifies into A times D over B times C. And there's, just so you know, there's another way of doing this called the disease odds ratio, which basically looks at what is the, in the exposed group, what is the risk of disease, and in the unexposed risk of disease. So basically, you could do this as A over B and C over D. But the important point is both an exposure odds ratio and the disease odds ratio end up with the same A times D over B times C. The point is, if you ever wanted to calculate your own odds ratio, you can do it for either direction with this formula. Okay? Didn't mean to confuse you, but just want you to know that those two terms exist. So the odds ratio, similar to the relative risk, is a way of comparing the odds in the unexposed to the odds in the exposed. And you can do this, the result basically gives you a sense, is the exposure harmful or protective? Same concepts, 1 greater than 1 less than 1. So just to take you through an example. So in this example, we're going to look at same disease, same exposure, but from a different perspective. So in this case control study, we're going to take people who have cardiovascular disease. So we're going to take 200 people, our cases, with cardiovascular disease, and 400 with no cardiovascular disease. So that's how we are starting our case control study, with these two groups. And we're going to look back into their records to a time before they had cardiovascular disease and see who was a smoker and who wasn't. So in the cardiovascular disease group, 112 were smokers, 88 were not. And in the no CVD group, 176 were smokers and 224 were not. So if we were going to calculate the odds of someone who has cardiovascular disease, what is their odds that they were a smoker? A over C. And then the odds that someone who does not have cardiovascular disease, what's the odds that they were a smoker? B over D. Same concept as in the other study, that basically we're going to put the odds, we're going to put the odds over each other, divide them, and we're going to get the odds ratio. So another way to calculate, you could do that, the A over C, B over D, or you could do this sort of just very simple A times D over B times C, and you'll get 1.6. So again, odds of developing cardiovascular disease were 1.6 times higher for smokers than non-smokers. It's kind of just a coincidence that they happen to be the same from the other study. The problems with the case control study was, again, that the disease already exists. So the temporal relationship is less clear. We believe that there's a cause and effect relationship, there's an association between cause and effect, but we can't prove it as clearly as we can with a cohort study because we don't know for 100% sure that we got the person's exposure before the disease. We think we did, but we may not have. And again, we have to look back, and the issues in terms of confounders is that they may not have been measured or measured correctly because we're relying on memory. And the biases in case control, so recall bias, again, those with disease are more likely to recall their exposures. And selection bias is, as I mentioned, how the controls are chosen compared to cases that they may be more likely to have the exposure just based on where you're selecting them. And then there's something else that I wanted to mention called prescription bias, which is also known as confounding by indication, which you guys will talk about in your small group, which basically is that if you're watching an exposure happen and the exposure you're thinking about is a medication, if we're not actively, like as researchers, giving that medication to people, they're choosing to take it, or their doctors are basically choosing to give it to them for some reason, there may be some reason why they're choosing that medication, meaning they maybe had like a negative outcome or a bad side effect with the other options that they had. Clinically, this will make more sense to you guys when you're taking care of patients, but if you choose to give your patient Tylenol instead of ibuprofen, it may actually be because they didn't like the ibuprofen to give them stomach pain. So there may be some other reason why they're using Tylenol And that stomach pain may have to do with the outcome, which was stomach cancer, something like that. So that's one other kind of bias that you guys are going to talk about a little bit in your groups. So again, we talked about the fact that the measure of association that we're using in a case control study is called the odds ratio, or the odds. And it's not as strong of association as risk. And, but sometimes people want to use a risk, or they would like to say that the risk of developing disease is X, Y, and Z based on a case control study. And there are situations when you can do that. And basically, if the disease is rare, and sort of by convention, that means that it's less than 20% of the population has the disease, that's sort of by convention considered rare, you could say that the odds ratio approximates the risk ratio, or the odds approximates the risk. But the other stipulation is that the sample has to be an unbiased sample for the population. So you're not going to necessarily need to do this or anything, but just so you know that occasionally people will do a case control study and will report a risk, and that may or may not be appropriate if the conditions may or may not be adequate for that. So the last kind of study that I want to mention is called a cross-sectional study. And this is also known as a prevalence study. And basically, a cross-sectional study is you take a population and you want to see at that time what data do you have for people having a certain exposure and a certain disease for individuals in that population. So basically, what you would do is say, we have, at this moment in time, say in Washington Heights, we have 1,000 people who have cardiovascular disease, 25,000 that do not, and when we look at which one of them smoke and don't smoke, the proportion is higher in the smokers. So it's kind of like a snapshot of one time in a population. It's not an attempt to collect data on exposures prior to the disease, or that attempt to sort of like go back to before and after. So it's basically can give you an idea that there might be an association, but it's not a particularly strong association because you're not trying to collect the data on exposures from before the disease developed. It's basically at one time. And again, because you are not going back in time to calculate, to look at the exposures, you can't calculate risk. Cross-sectional studies are using odds ratios as well. And again, you can sort of calculate the odds ratio of disease or exposure. Just important for you to know that that exists. So I'm going to conclude just by making these points again, that observational studies are necessary to determine if associations exist between exposures and outcome, and particularly for things that can't be randomized, things we cannot do to people, so conditions, harmful things. Cohort studies will be able to calculate a risk ratio because they're going forward, and we can use number needed to harm or number needed to treat based on a risk ratio. Case control and cross-sectional studies cannot calculate risk ratios or number needed to harm, number needed to treat, but they can calculate odds ratios. And confoundings are the factors that come with people, have to be measured and controlled for in your analysis. And biases are fundamental flaws in this design studies that affect the results and can't be controlled for. So I'm going to stop there. I know that's kind of a lot of information. And take any questions that you guys might have. Feel like you can ask anything. A lot of blank stares. Yes.
I had a question about loss to follow-up.
Yes.
What happens when you have, in a prospective study, when you have two groups and smoking, for example, when you have either somebody who's a smoker who quit smoking or somebody who wasn't smoking in a 10-year study and then 5 years through starts to smoke.
So what you're talking about is actually called crossover, probably, meaning you didn't have the exposure at the beginning, but you move over into the exposure group. Usually those people are counted in the non-exposed group, even though they chose to start smoking. Yeah, go ahead.
So Actually, over the years, we've developed statistical techniques to deal with that, and that's a time-varying covariate. So essentially, by now, we have easy-to-apply models that take into consideration how an exposure changes over time, and the adjusted risk estimate will include that in consideration. So the problem is when you lose people to follow up based on who they are, and the fancy name for that is informative censoring. That can be really bad because sometimes it's not clear that the proportion of people dropping out is quite different. There might be a slight difference, but there might be a selection process in terms of who drops out. And a very good example of that is when people look at studies, even randomized controlled trials, of studies to lose weight. People who are ashamed because they haven't lost enough weight don't tend to come back. So there tends to be an inflation of efficacy estimates because people who come back are happy because they lost the weight, and that's why they're coming back. And then you report those data, and you've got informative censoring. So you're too optimistic in terms of what happened. The opposite can be true also. You implement a new intervention that looks fantastic, and unbeknownst to you, it's causing a lethal side effect, and people drop out because of that. And sometimes the death certificate information may be uninformative. We've had cases, for example, in studies of antiarrhythmics many years ago when people dropped dead when they were driving, and the cause of death in the death certificate was MVA, motor vehicle accident. And it took an all-cause mortality analysis by other investigators to actually notice the fact that people in that intervention group were dying more frequently, even though it was known as non-cardiac deaths.
So yeah, the answer to your question was that the statistics that you guys will learn some about, there's like a whole slew of statistics that you could use to try to control for things that are more complicated. The key thing is, can you measure it, and do you know that it's happening? Because if you know that it's happening, you can control for it. If you don't know that it happened, then you have to sort of assume that they stayed in the same group. Anything else? Okay. Yeah.
For the cohort studies and the case control trials, when you're talking about risk and odds, you have the time, like the 1 year in it.
Yes.
I'm curious about for cross-sectional studies.
Yeah, there's no time associated with it. It's just at this time, sort of, there's no way, there's no like distance of time you've been watching them. So that's the whole point about why cross-sectional studies are kind of weaker, because or the other way to think of it is prevalence study. Sort of prevalence meaning like how much disease exists in our population, and could there be an association with a certain exposure? Maybe. We think more smokers seem like they have more cardiovascular disease at this point, but we haven't separated out the time, the cause and effect. So a lot of times cross-sectional studies can give us a hunch that there's an association and be sort of the first step to then design either a case control or a cohort study, because it seems like there's an association based on like right at this, if we were to look now, you know, most of the people who have cardiovascular disease seem like they smoked at some point, but we didn't collect the data about like when they started and did they have cardiovascular disease then, that kind of thing. So cross-sectional studies are quick and easy ways to get sort of like an idea of whether or not there's an association, but usually lead to a more in-depth study after that. That makes sense, because you're right, there's no time that come with it.
So actually, you know, a very good example of a big failure of a cross-sectional study is if you look at something that kills people very quickly. If you look at cyanide exposure in big amounts, people die very quickly, so the prevalence of people exposed to cyanide is going to be low because most people have already died. So high fatality rate is actually a huge limitation when you do a cross-sectional. Cross-sectional studies capture best things that tend to be prevalent because the timeline for fatality is very long.
They're living with it. Okay. Anything else? Great. Thanks. It wasn't too confusing, sure. I hope it wasn't too confusing. I wanted to say it a couple times. Like, there are courses.